Welcome back, grade 9s. Here we are at our polynomials unit. I'm going to be covering a review of what you did in class before we left for our pandemic break. And I'm also going to be covering new material on multiplying, dividing polynomials. Here is our chapter list. I have added a pre-unit review, which I'll be covering in this video. There's also polynomial introduction with terms, algebra tiles, adding polynomials, multiplying polynomials, which is our new unit here. This is what we did not cover yet in class, and dividing polynomials, and then some big questions to finish off our unit. So we're going to start with our pre-unit review. So recall the commutative rule. Now we talked about this a lot in class, but I really want to have a chance to review it with you online right now. So can we change our terms around and get the same answer? Let's take a look at 3 times 5. And I'm going to change my terms around. So now I have 5 times 3. Those both equal 15. This is a true statement. How about with negative values? Negative 4 times 5. I'm going to change these terms around. I'm going to keep the negative with the 4 because that's my term value. So now I have 5 times negative 4. Let's see. Both of them equal negative 20 is also true. Is this true for additive operations? So adding and subtracting. Let's take a look. And I'm going to go negative 5 plus negative 3 plus 5. Okay, so notice that the negative is sticking with that 3 because in the end, this value, this term, is a negative term. It's a negative value, negative 3. So when I switch it around, the negative is still sticking with it. It's still a negative 3. And that is why when I can move these terms around, it'll still equal the same answer of 2. This is known as the commutative rule, and we're going to use it a lot in our polynomials unit. So as long as the negative sticks to its number, you'll be happy. Review. Recalling the commutative rule continued. Does it work for more than 2 terms? Let's find out. Here I have 3 times 5 times 4. And I just rearranged it randomly to 5 times 4 times 3. Notice that they all equal 60. Nothing has changed, just how they look. So this is true. Let's take a look at negative 2 times 10 times 1/5. Rearranged everything. Now notice that 10 times 1/5 is just going to be 2, and then times negative 2 is going to give us a negative 4. This is true in both statements, and therefore is true for our commutative rule. Now we have 8 plus 5 minus 2. I'm going to rearrange it. Remember that I keep my negative attached to my 2 here. So there it is. And equals 11. This is true. So our commutative rule can work for more than just 2 terms. All right, now we need to recall exponents. It's been a while. We used the commutative rule with our exponents unit already. So we take a look at 3 times x to the power of 3 times 4 times x to the power of 4. Now, I'm going to use our commutative rule to break apart everything here as a product and put my whole numbers together, my 3 and a 4, and put my variables together. So kind of my like terms. 3 times 4 is going to be 12, and then we use our exponent rule where we have the same base and we're multiplying, and now we'll add our exponents together. If you are confused about that, I would recommend going back into our exponents unit and reviewing a little bit of those rules. So 12x to the power of 7, or 12 sets of x to the power of 7. The commutative rule and exponents will come up often in this unit, so it's important that we get some practice in. Let's take a look at 8 times x to the power of 10 divided by 2 times x to the power of 3. I'm going to rearrange. Now, there's plenty of ways to visually make this look better. What I'm doing now is I'm splitting up my common terms, so my 8, my 2, and my variables. Now, the division sign is keeping itself between the two values here. So I color-coded it for you. So 8 divided by 2 is 4, and x to the power 10 divided by x to the power 3, that is going to be the same base with exponents, and with division we subtract. So here I am subtracting my exponents. We have 4 times x to the power 7, or 4 sets of x to the power 7. Okay, and then I'm showing you another visual for this. So some people like to stack it. I definitely like to do that. It's a little more visually appealing. Continuing our exponents. Recall that common bases with the same power can be added together. So here we have two bases. Now, there's 3 sets of x squared and 2 sets of x squared. So how many sets in total of x squared are there? I hope you notice that there's 5. So as long as we have the same variable, we can use an additive operation to just add everything together. So 5 sets of x squared. But if that base does not share the same power, they cannot be added together. Okay? This case here, you need to understand that when we're squaring something, this is a completely different number often than it would be if it was not squared. There are some exceptions to that, but we don't know what x is, and so we separate them. So in this case, I have 3 x squareds and 3 x's. This would be as compressed as I can make this expression. That is because x squared and x are likely different values and therefore cannot be shown as a set. So I'm going to show you an example here. Let x equal 3. If x equaled 3, then x squared is going to equal 9. They are completely different values. That's why we cannot put them as a product together. Okay, that ends your pre-unit review.